Alright class, in our last toolbox, we introduced the derivative of a function, and we discussed how we can use derivatives to quantify the growth rate of an organism if we know how its population changes with time. We can also think of the derivative with respect to a moving object. If we define a function that describes the position of an object as a function of time, then the derivative of that function is the object's velocity. We also discussed the geometric definition of a derivative, which tells us that the derivative of a function is the slope of a line drawn tangent to a curve. In this toolbox, we're going to build on the intuition that we developed for derivatives and apply the definition of a derivative to actually start computing some derivatives. We'll then start working on the derivatives of some of the elementary functions that we discussed earlier in the course. Alright, in our last toolbox, we defined the derivative of a function f of x as the limit as h approaches 0 of f of x plus h minus f of x all divided by h. But we didn't actually talk about what a limit is. So let's talk about that now. The limit of a function f of x, as that function moves closer and closer to x being equal to a, will be equal to the value L if for every small number epsilon that is greater than 0, we can also find a small number delta that is greater than 0, such that you can write a pair of inequalities stating that when the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than that small value of epsilon. If we cannot find some such value of L, then we say that the limit of f of x as x approaches a does not exist. Okay, that's a very technical and kind of confusing definition. So let's go through an example to see how it works and what it actually means. Consider the function f of x equals x squared minus 4 divided by x minus 2. If we ask what this function is going to be equal to at x equals 2, and we plug that in, we have 2 squared minus 4 divided by 2 minus 2, which is equal to 0 over 0. 0 divided by 0 is, of course, undefined. So the value of f of 2 is not defined. It's not a real number. However, if we plot f of x, we can see that the function is defined everywhere else. And everywhere else it is just equal to the function f of x equals x plus 2. The fact that f of x equals x plus 2 everywhere else actually makes a lot of sense if we take a moment to stop and think about that function. You see, we can actually rewrite f of x as x minus 2 times x plus 2 divided by x minus 2. Since we have x minus 2 in the numerator and the denominator, we know that they cancel each other out, so this function should be equal to x plus 2 everywhere except at the value x equals 2, since, as we already determined, f of x is undefined at that value of x. Alright, looking at that graph, or at the equation of f of x, we can see that although our function f of x is undefined when x equals 2, as x approaches 2, our function approaches the value of 4. Therefore, we say that the limit of f of x as x approaches 2 is equal to 4. Alright, how does that relate back to our definition of the limit? Well, in this case, we're calculating the limit of f of x as x approaches 2, so that means a equals 2. And we've already decided that the limit of f of x as x approaches 2 is equal to 4, which means that L equals 4. So now we need to find some small value epsilon and some other small value delta, so that whenever the absolute value of x minus a is less than delta, then the absolute value of f of x minus L must be less than epsilon. Okay, let's give this a try. Let's decide to use the small value of 0.1 for epsilon. We thus need to ask the question, is there some small value of delta such that if x is less than delta away from 2, then f of x is less than epsilon away from 4? Well, let's try out a small delta of 0.05. We're thus really asking, for all possible x's between 1.95 and 2.05, is f of x between 3.9 and 4.1? Well, let's give it a try by plugging in some values. F of 1.95 is equal to 3.95, so that's within our allowed range. F of 1.97 is equal to 3.97, so that's good. F of 1.99 equals 3.99. F of 2.01 equals 4.01. F of 2.03 equals 4.03. F of 2.05 equals 4.05. All of those are falling within our allowable range, so that seems to work. But our question isn't just, is there some epsilon and some delta for which this works? It's, can you find a delta that will work for any possible small epsilon that might be chosen? So let's try this again. And this time, let's pick a much smaller value of epsilon, which equals 0.001. So let's similarly pick a smaller value of delta equals 0.0005. This means that if our limit as f of x approaches 2 really is 4, then for all x between 1.9995 and 2.0005, then f of x must be between 3.99 and 4.001. So let's plug in values again and see if this works. When we plug in those values ranging from 1.9995 to 2.0005, we get 3.9995 to 4.005, all within our allowable range. So this does seem to work again. Really, we need to be sure that this works with any arbitrarily small epsilon, but it's already pretty clear that this will always work. So our limit as f of x approaches 2 really is equal to 4. Okay, so that's how we used the technical definition of a limit. But that can be a little bit confusing. So let me introduce a more intuitive definition of the limit. It won't quite be the technical definition of a limit, but it'll be close, and it should be more intuitive. Basically, let's create this intuitive definition by saying that if the limit as x approaches a of f of x equals L, then if x1 is closer to a, and you choose a new, if x1 is close to a, and you choose a new x2 that is even closer to a, then either f of x2 is closer to L than f of x1, or f of x1 and f of x2 both equal L. So let's plug in and see how this intuitive definition might work. First, let's choose a value of x1 equals 1.999. In that case, we have f of x1 equals 3.999, which is definitely pretty close to 4. But if we choose an even closer value of x2 equals 1.9999, then f of x2 equals 3.9999, which is even closer to 4. So that seems to work. Please note that this is not the technical definition of the limit, because it only works if we are sufficiently close to a. However, we don't necessarily know what sufficiently close to a means. Nevertheless, I think this is a very intuitive way to think of the limit that will help us understand it as we apply it to the derivative, which is our next step in this toolbox. Alright, remember that our definition of the derivative is that the derivative of a function f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So let's look at this function f of x equals x squared, and let's try to find its derivative at the point x equals 2. Alright, so using the equation above, we know that the derivative evaluated at x equals 2 is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 all divided by h. We can plug in that f of x equals x squared to see that the derivative is equal to the limit as h approaches 0 of 2 plus h squared minus 2 squared divided by h. So remembering what our limit means, we need to think about what this will be equal to when h gets really, really small. So let's try plugging in a small value for h. Let's try h equals 0.01. In that case, we have 2 plus 0.01 squared minus 2 squared all divided by 0.01, which is equal to 4.01. But of course, we know that the limit should still be approaching the true value as we make h even smaller, so let's try plugging in h equals 0.001. In that case, we find that 2 plus 0.01 squared minus 2 squared divided by 0.001 is equal to 4.001. It seems like as h approaches 0, we're approaching the value of 4. So a likely guess for the derivative of f of x evaluated at x equals 2 is 4. But that's really just an educated guess at the limit. Let's take a look at this in a different way. Let's try expanding our limit equation to try to get a truly exact estimate. Alright, 2 plus h squared minus 2 squared all divided by h is equal to 2 squared plus 4h plus h squared minus 2 squared all divided by h. Well, first off, we know that 2 squared minus 2 squared will cancel out, so we can get rid of those terms, and we've now got the limit as h approaches 0 of 4h plus h squared divided by h. First, let's note that when h equals 0, 4h plus h squared divided by h will be equal to 4 times 0 plus 0 squared divided by 0. And that, of course, equals 0 divided by 0. So when h equals 0, that is undefined. However, if h is not equal to 0, we can write that 4h plus h squared divided by h equals 4 plus h. So that will be true for any h except when h is exactly equal to 0. This means that as h gets really small, we're going to approach the value of 4. Of course, that's the definition of how the limit works, so we can write that this limit over here is exactly equal to 4. Note that our new exactly calculated value is actually the same thing as what we estimated before, so that's encouraging. Also remember from our geometric definition of the derivative in the last toolbox that 4 is equal to the slope of a line drawn tangent to that curve. Alright, we've gone through the logic of using the limit definition to calculate the derivative when x equals 2. Next, let's apply this same logic to calculate the derivative of this function at any point. We start with our same definition of the derivative, but this time we're not substituting anything in for x. We're keeping the x in the equation. When we actually substitute in that our function is equal to x squared, we get the limit as h approaches 0 of x plus h squared minus x squared, all divided by h. If we again expand this equation, we find that the derivative is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, all divided by h. We can see that x squared minus x squared will cancel out, leaving us with the limit as h approaches 0 of 2xh plus h squared on h. The term 2xh plus h squared will be undefined if h is equal to 0, but if h is not equal to 0, it will be equal to 2x plus h. Thus, as h approaches 0, 2xh plus h squared over h will approach 2x. And we can write the derivative of f of x with respect to x is equal to 2x. We can also go ahead and plug in 2 for this equation and evaluate the derivative at x equals 2, and we find that it is equal to 2 times 2, which is 4, or in other words, the same thing that we calculated before, which of course is reassuring. We've now figured out a general equation for the derivative of f of x, and we can use this equation to calculate the derivative at any point. We can also compare the derivative we calculate with this equation to the derivative we calculate as the slope of the tangent line, like we did in the previous toolbox. And of course, as I suspect you guessed, we find the exact same answer using both approaches. The derivative of x squared is 2x, and we were able to calculate this using our limit definition of the derivative. Next, let's use the same approach to figure out a general equation for the derivative of a polynomial. As a reminder, we talked about polynomial functions in Toolbox 2.2. Polynomial functions are functions that have only non-negative powers of their input variable. They include linear functions, quadratics, cubics, quartics, etc. We refer to a polynomial function as a polynomial of degree n if n is the largest exponent in the equation. The basic equation of a polynomial is f of x equals a subscript n times x to the n plus a subscript n minus 1 times x to the n minus 1 plus dot 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 plus a2x squared plus a1x plus a0. In this case, f of x is an n-degree polynomial because the largest exponent is n. Let's start with a simple n-degree polynomial. F of x equals a subscript n times x to the n. We'll use our limit equation for the derivative, and then substitute in a subscript n x to the n for f of x. We can then expand the term a subscript n x plus h to the n using the binomial theorem, which you can look up if you want. Using this theorem, which basically is a formula for performing the multiplication of x plus h times itself many times, we'll get the formula x to the n plus n factorial over n minus 1 factorial, x to the n minus 1 h plus n factorial over n minus 2 factorial times 2 factorial times x to the n minus 2 times h squared plus dot 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 plus n factorial over 2 factorial times n minus 2 factorial times x squared times h to the n minus 2 plus n factorial over n minus 1 factorial x times h to the n minus 1 plus h to the n. Now this may look a bit complex, but it actually simplifies pretty easily. First, like before, we see that we have an a subscript n x to the n on the left side minus a subscript n x to the n on the right side, so those will definitely cancel out. Now looking at this equation, we have a whole bunch of terms with h in them in the numerator, and we have h in the denominator, so we can divide the entire numerator by h, which generally means that we're just decreasing the exponent on the h by 1. Now if we look at this equation, we see that every term in it still has h except for the leftmost term. That means that as h goes to 0, all of those other terms will also go to 0, and we're going to be left with only that leftmost term. Since all that we have left is this term here, we know that the entire limit term, and in fact the entire derivative, must be equal to a subscript n times n factorial over n minus 1 factorial times x to the n minus 1. And then, since n factorial over n minus 1 factorial is simply equal to n, we know that the derivative is equal to a subscript n times x to the n minus 1. This is a really important equation because it tells us the derivative of any generic function of the form a constant times the input variable raised to any exponent. This is one of the derivative equations that you will wind up using the most, and one of the ones that you should probably commit to memory. The derivative of a function that is any constant times x raised to any exponent is simply equal to the constant times the exponent multiplied by x raised to the exponent minus 1. For instance, earlier in the lecture, we looked at the derivative of the function f of x equals x squared. We can use the equation we just derived by noting that a subscript n equals 1 and n equals 2. When we then plug this into our equation, we find that the derivative of f of x equals 2 times x to the 1, which of course is equal to 2x. And that of course is the exact thing that we calculated early in the toolbox, so that's good. Next, let's try some other function. Let's try the function g of x equals negative 5x to the 9th. In this case, we know that a sub n will be equal to 5 and n will be equal to 9. We can therefore easily plug in our equation for the derivative of a polynomial function with those values of a subscript n, and we find that the derivative is equal to negative 5 times 9x to the 8th. And of course, that's equal to negative 45x to the 8th. And if we wanted to know what the derivative of that function is when x equals 2, all we would need to do is plug in 2 instead of x, and we'd find that it is equal to negative 45 times 2 to the 8th, which is equal to negative 11,520. All right, that's great. we've got a nice, easy way to find the derivative of any function that is simply composed of a constant times x raised to an exponent. But remember that a polynomial can actually have many such terms added together. So how do we find the derivative of that function y of x when there are many of these terms added together? Well, to figure this out, we're going to need to talk about taking the derivative of the sum of two functions. Let's write a function that says f of x equals the sum of two other functions, g of x and h of x. For now, we don't know what g of x and h of x actually are. We just know that they are both functions of x. So how do we find the derivative of f of x? Well, let's use our limit definition of the derivative again. When we actually plug in f of x into this limit equation, we find the derivative of f of x is equal to the limit as h approaches 0 of g of x plus h of x plus h minus g of x plus h of x all divided by h. And we can actually pretty easily rearrange this equation to find that the derivative is equal to the limit as h approaches 0 of g of x plus h minus g of x plus the limit as h approaches 0 of h of x plus h minus h of x divided by h. Okay, why did I go through the bother of rearranging this? Well, if you look carefully at this equation and also look back at our limit definition of the derivative, you'll see that the left-hand side of this equation is equal to the derivative of g of x, and the right-hand side of the equation is equal to the derivative of h of x. We can therefore write that the derivative of f of x is equal to the derivative of g of x plus the derivative of h of x. This is a very useful general equation. This equation allows us to figure out the derivative of the sum of any functions as long as we can figure out the derivative of each part of the function. For instance, during problem set 3, when you're asked to write a function to describe how carbon dioxide varies as a function of time, as measured by Charles David Keeling on Mauna Loa, many of you wrote a function that generally looked something like this. F of t equals 2.5 sine of 2 pi t minus 1 over 12 plus 315 times e to the 0.0044 times t minus 1960. If we wanted to take the derivative of this equation with respect to t to figure out how fast the carbon dioxide concentration is changing as a function of time, we could break this function up into two simpler functions. We could say that g of t equals 2.5 sine of 2 pi t minus 1 over 12, and that h of t equals 315 times e to the 0.0044 times t minus 1960. We could then apply our equation for the derivative of the sum of functions to determine that the derivative of f of t is simply the derivative with respect to t of these two simpler functions. In our next toolbox, we'll talk about how to compute these simpler derivatives of a sine function or an exponential function. But first, let's get back to our generic equation for a polynomial that motivated this discussion. Alright, let's break this equation down into a bunch of smaller functions, each of which we know how to take the derivative of. First, we'll write that g of x equals a subscript n times x to the n, and we know how to take the derivative of this function. It is simply equal to a subscript n times n to the x, a subscript n times x to the n minus 1. Next, we'll write that h of x equals a subscript n minus 1 times x to the n minus 1, and we can compute that its derivative is a subscript n minus 1 times n minus 1 times x to the n minus 2. Our next function will be j of x equals a2x squared, which has a derivative of 2a2 times x to the 1. We'll then say that k of x equals a1 x to the 1, which has a derivative of 2a1 x to the 0. And since x raised to the exponent of 0 is simply equal to 1, we know that this derivative simplifies to 2a1. Finally, we'll write that m of x equals a0 times x to the 0. Note that I'm writing it like this because, of course, multiplying by x to the 0 is simply multiplying by 1. But putting it in this form, we can take the derivative using the equation we used before. When we apply that equation, we find that the derivative is equal to 0 a0, x to the negative 1, and of course anything multiplied by 0 is simply 0, so that term will go away. Of course, that actually makes a lot of sense. If m of x is actually just a constant value, then its derivative will be 0 because it isn't changing. For instance, if we say that the percentage of oxygen in the atmosphere is a constant 20.95%, then its derivative with respect to time will be 0. So our equation is definitely making sense so far. Alright, now let's use that rule we learned about the derivative of the sum of two functions to write that the derivative of y of x equals the derivative of g of x plus the derivative of h of x plus the derivative of any extra terms that might be in between plus the derivative of j of x plus the derivative of k of x plus the derivative of m of x. And since we've already calculated those other derivatives, we can go ahead and plug them in. We see that the derivative of y of x equals a subscript n times x to the n minus 1 plus a subscript n minus 1 times x to the n minus 1 plus dot 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 plus 2a2x plus 2a1 plus 0. That's now a very general equation that we can use for computing the derivative of any polynomial function. Don't forget this equation because there are many times when we want to find the derivative of functions that are some variation of a polynomial. Alright, let's briefly review the material that we've covered in this lecture because it's quite important and we'll use it many times in the coming toolboxes and problem sets as we work to study a changing environment. We started off by remembering our definition of the derivative, which tells us that the derivative of the function f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Next, we investigated the limit and basically decided that we could think of the limit as being the value that f of x approaches as x gets closer to a if f of x continues to get closer to that value L as x gets closer and closer to a. We then used our understanding of the limit to derive some very important equations that will keep coming back. We determined the summation rule for derivatives that tells us that if f of x is equal to g of x plus h of x, then the derivative of f of x is equal to the derivative of g of x plus the derivative of h of x. We also determined that if g of x is a simple polynomial such that it's equal to a constant value a times x raised to the exponent of n, then the derivative of g of x with respect to x is equal to the constant a times the exponent n multiplied by x to the n minus 1. And finally, we derived a general equation for the derivative of any polynomial function. Please note that it's not necessary for you to remember how we did these derivations. That's not the goal of this course. The goal of this course will be to use the equations we've derived here in future toolboxes and in the problem sets as we try to understand our changing Earth system. Don't forget to take the mini quiz before class.